When you design an LNG or LPG marine transfer facility, start with one fact. The ship-shore interface is a moving boundary carrying high-energy hazardous inventory. You are transferring refrigerated or pressurized liquefied gas at high flow rates between a fixed terminal and a vessel affected by wind, tide, current, mooring behavior, ship motion, and human operation. The emergency shutdown system is therefore not just a shutdown button. It is a sequenced safety architecture designed to stop transfer, isolate inventory, control surge, protect the loading arm, and prevent escalation. The core philosophy is built around two levels, ESD-1 and ESD-2. ESD-1 is the first stage emergency shutdown. It stops the cargo transfer operation in a quick, controlled manner by closing shutdown valves, stopping transfer pumps, opening spillback where required, and coordinating ship and shore actions. ESD-2 is the second stage emergency shutdown. It includes ESD-1, but also activates the loading arm emergency release system. The ERS closes isolation valves on both sides of the emergency release coupler and then disconnects the loading arm from the ship with minimum spillage. So keep the distinction clear. ESD-1 stops transfer, ESD-2 stops transfer, and disconnects the arm. Not every emergency needs disconnection. But if the vessel drifts, the arm approaches its operating envelope, or the manifold and arm are at risk of mechanical damage, stopping flow is not enough. You must isolate and release before the loading arm becomes the failure point. An ESD-1 can be initiated manually or automatically. Manual initiation is normally by emergency push buttons at the jetty head, jetty control room or cubicle, trestle approach, main control room, and from the ship through a ship-shore link or pendant box. Automatic initiation may come from fire detection, high level, high pressure, low hydraulic pressure, loading arm pre-alarm overextension, rupture or loss of ship-shore link, ESD-2 activation, fuse failure in the safeguarding logic, power failure, or terminal-specific process trips. The purpose is simple. If continued transfer becomes unsafe, the system must stop the operation without waiting for operator discussion. But the engineering is not simple. An emergency shutdown is not just fast closure. It is controlled closure. If valves close too fast in high-rate liquid transfer, surge pressure can exceed piping or equipment design limits. If pumps stop in the wrong sequence, hydraulic shock can occur. If ship valves close faster than terminal valves, the shore system may see excessive surge. If shore valves close too fast during unloading, the ship system may see excessive surge. The ESD system must act quickly, but not blindly. At export terminals, shore pumps drive product to the vessel. Flow stoppage normally requires fast closure of shore ESD valves, typically around 10 to 15 seconds, stopping the loading pumps and opening pump spillback valves immediately. Spillback gives the pump flow a controlled path and helps reduce surge effects. At import terminals, the ship pumps drive product to shore. The ship's manifold valves close within the required shutdown time. Ship discharge pumps stop, and shore ESD valves are normally slower closing, often around 30 to 60 seconds, to reduce surge in the loading arm and receiving line. This distinction is critical. Export terminal, shore pumps dominate the hydraulic energy. Import terminal, ship pumps dominate the hydraulic energy. You cannot copy the export shutdown philosophy into an import terminal without checking the transient behavior. The ship-shore link is central to safe ESD performance. During transfer, ship and shore become one hydraulic system. If the ship trips and shore continues pumping, the system is exposed. If shore trips and the ship continues discharging, the system is exposed. If one side closes valves without coordinated pump response, surge risk increases. A compatible ship-shore link allows either side to initiate shutdown and makes the other side respond immediately. For LNG, a delay-free link is essential. For LPG, it is strongly recommended where operating conditions and vessel compatibility justify it. Where compatible ship systems are not available, a pendant box can be placed on the ship so ship personnel can initiate shore ESD-1 directly. The engineering principle is this: the side that first detects the emergency must be able to stop the transfer. Now consider the ESD valves. ESD-1 valves must be remote-operated, fail-safe, fire-safe, tight shutoff valves. They should close automatically on loss of actuating power. They should not depend on hand wheels or lever operators for emergency action. Pneumatic or hydraulic spring-to-close actuators are typically used. Valve closure time must be adjustable but protected against unauthorized change. This matters because valve closure time is not only a mechanical setting, it is part of the surge design basis. If the surge study assumes a defined closure time and the actuator speed is later changed in the field, the original safety calculation may no longer be valid. Also, distinguish total valve closure time from effective valve closure time. Total closure time is the full travel from open to closed. Effective closure time is the part of the stroke during which flow actually reduces from about 90% of steady flow to zero. This varies by valve type. Gate valves reduce flow very late in travel. Butterfly valves reduce flow over a wider closing range. Ball valves normally give a smoother closure characteristic and are often preferred for ESD service from a surge control point of view. For liquid loading lines at export terminals, 2 ESD valves in series are commonly used near the jetty head. This provides smoother shutdown, backup if one valve fails, and double block isolation for downstream jetty piping. Vapor return lines normally use 1 ESD valve located in a safer area away from the immediate jetty head, with consideration of non-return protection near the arm or manifold. For liquid discharge lines, at least 1 ESD valve and a non-return valve are required. The non-return valve limits backflow during shutdown and protects the system when ship pumps stop or when shoreside pressure conditions change. Valve location is not arbitrary. ESD valves are located away from the immediate jetty head so that, in a jetty emergency, the long pipeline inventory does not continue feeding the hazardous area. Now ESD-2. ESD-2 exists because the loading arm is connected to a moving vessel. Even a well-moored ship can move due to wind, tide, current, passing vessel effects, or mooring failure. If the arm exceeds its design envelope, mechanical failure may occur at the arm, manifold, flange, or piping. The emergency release system prevents this by isolating and disconnecting the arm. The ERS consists of an emergency release coupler and 2 isolation valves, one upstream and one downstream of the coupler. Before the coupler opens, both isolation valves must close. This creates the dry brake function. The sequence is essential. First, initiate ESD-1. Second, close the ERS isolation valves. Third, confirm isolation by interlock. Fourth, release the coupler. Fifth, activate surge relief if installed. Typical ERS isolation valve closure may be around 5 seconds, with the coupler releasing within about 2 seconds after valve closure. This gives rapid disconnection when the ship is drifting, but it also creates surge risk. Any ERS closure time must therefore be checked against ship and shore piping design pressure. Fast disconnection without surge verification is not safe design. ESD-2 can be initiated manually from protected shore push buttons at manned locations. It is normally not initiated manually from the ship, especially in LPG service, because this increases the risk of spurious trips and human error. Automatic ESD-2 is initiated from loading arm apex or slewing angle over extension signals. The loading arm protection normally uses 2 stages. The pre-alarm occurs before the arm reaches the design limit. It initiates ESD-1 and warns that the arm is approaching the edge of the operating envelope. The trip alarm occurs closer to the mechanical limit. It initiates ESD-2 and activates the ERS. Pre-alarm means stop transfer. Trip alarm means disconnect before damage. That is the correct escalation philosophy. Because ESD-2 can physically release a heavy loading arm assembly, accidental activation must be prevented. Manual ESD-2 push buttons must have protective covers. The arm must have a parking or storm lock with position indication. Logic must inhibit ESD-2 when the arm is parked or secured. A warning light should indicate when the parking lock is not secured and the ERS hydraulic system is live. A key-operated hydraulic supply valve adds another safeguard. When the arm is parked or maneuvering, hydraulic supply to the ERS is isolated and the key is trapped. When the arm is connected to the ship, the valve is opened, the key is transferred to the arm control unit, and the arm can be placed in freewheeling mode. The loading arm has 2 main control modes. Mode 1 is freewheeling, used when the arm is connected to the ship manifold. Mode 2 is parking or maneuvering, used when the arm is parked or being moved. Opening the loading MOV should only be possible in freewheeling mode. When the arm is switched to parking or maneuvering mode, the loading MOV should close if it is not already closed. Manual ESD-2 should only be possible when the arm is in the correct operating condition. parking lock not closed, at least one loading MOV not closed, arm not in parking or maneuvering mode, test override not active, and ERS hydraulic supply open. Automatic ESD-2 should only be possible when the parking lock is not closed, the test override is not active, and the ERS hydraulic supply is open. This is how accidental release is prevented, not by relying on memory, but by hard interlocks. Each loading arm should have loading MOVs at the manifold connections for primary isolation. These valves need closed and not closed feedback, and those signals must be part of the safeguarding logic. If all loading MOVs on an arm are closed, an overextension pre-alarm may not need to initiate ESD-1 because no transfer path is open. But if any loading MOV is not closed and the arm reaches pre-alarm, ESD-1 must initiate. In multi-product arms, vapor liquid arms, and piggyback arrangements, logic must prevent unsafe valve combinations. Normally, only one loading MOV on an arm should be open at a time, unless the design specifically permits otherwise, with proper safeguards. The more flexible the arm, the stronger the interlock philosophy must be. Now, surge protection. Surge is one of the most critical design constraints in LNG and LPG transfer. When liquid flow in a long line is stopped quickly, the moving liquid column generates transient pressure waves. These can exceed line design pressure, damage valves, overload supports, and stress loading arms. At export terminals, ship manifold valve closure time must be checked against shore ESD valve closure time. Ship valves should not close faster than shore valves in a way that exposes shore piping to excessive pressure. Before loading, ship valve type, closure time, and terminal closure time should be compared. Loading rate must be adjusted if needed. Safe loading rate is not just pump capacity. It depends on valve type, effective closure time, piping volume, line profile, surge calculation, and ship-specific behavior. Where required, export terminals use a surge relief system. This may include a fast-opening dump valve to a surge drum, backed up by a relief valve. The dump valve opens on ESD-2 or high-pressure detection and diverts liquid while ERS and ESD valves close. After ESD valve closure, the dump valve closes. The relief valve protects the system if the dump valve fails or if ship valves close unilaterally. The surge drum must be sized for normal operating volume, loading arm drainage volume, and surge volume. High level in the surge drum should initiate ESD-1, and that action must be fail-safe or redundant. At import terminals, the main concern is shore valve closure while ship pumps are still operating. The minimum allowable effective closure time of shore ESD valves must be determined during design. Once set, no other shore valve should be capable of closing faster in a way that creates unacceptable surge. Ship pump trip must also be studied, especially where elevation differences exist. If pump trip can create surge above design pressure, either the design pressure must be increased or the discharge rate must be limited. Surge analysis is not an appendix. It governs valve speed, loading rate, relief capacity, surge drum sizing, and operating limits. Now the logic system. ESD logic should follow fail-safe signal philosophy. In the normal condition, safety inputs are healthy. If a required healthy signal is lost or interrupted, the output changes state and initiates shutdown. Latching is required so that once an ESD occurs, it remains active until reset deliberately. The operator must be able to identify the trip source before reset. Resetting without diagnosis is poor operation. Resetting without correction is unsafe operation. The ESD-1 logic receives inputs from push buttons, fire alarms, ship shore link, hydraulic low pressure, loading arm pre-alarms, ESD-2 output, surge drum high level, tank level and pressure trips, and other terminal-specific signals. The ESD-2 logic should be arm-specific. Each loading arm should have dedicated logic for ERS valve closure and coupler release. Automatic ESD-2 should normally release only the affected arm. Manual ESD-2 may release all connected arms depending on the design state. Each loading arm should have dedicated safeguarding logic split into ESD-1 and ESD-2 sections. Safeguarding functions must be fail-safe. For critical single-arm installations, redundancy should be considered. Line monitoring should be considered where practical. Hydraulic integrity is another key requirement. The ERS depends on hydraulic actuation, so the hydraulic system must retain pressure long enough to execute emergency release after defined power failures. A retention capability of around 3 hours gives time to restore power or manually unbolt the ship manifold if required. The system should alarm AC or DC power failure. Reliability can be improved by dual hydraulic pumps, separate electrical feeders, hand pump backup, nitrogen accumulator backup, and leak-tight directional valves. But backup systems only count if tested. A weak accumulator, low nitrogen precharge, leaking valve, or stuck solenoid is not redundancy. It is hidden failure. Quick connect, disconnect couplers should be treated carefully. Bolted flanges with mechanically interlocked ERS valves and couplers are often safer and more robust. QCDC may look faster, but the time saving is often not decisive because connection and disconnection occur alongside cargo talks, safety checks, and documentation. If QCDC is used, disconnection must only be possible when all loading movies are closed. If fitted with ERS, inadvertent opening should be linked to closure of the shipside ERS isolation valve to minimize spillage. If no ERS is fitted, integral valve interlocks are needed to prevent disconnection with the valve open. Now overrides. The operational override switch, or OOS, is mainly used in refrigerated product service to allow cold circulation through loading and discharge lines when no ship is connected. This prevents thermal cycling. But OOS must be interlocked so that ESD valves can open only when all loading movies are closed. It may override expected post-loading conditions such as loss of ship shore link and low hydraulic pressure after hydraulic pumps are stopped. OOS is useful, but it is also a controlled defeat. It must be visible, interlocked, and understood. The test override switch, or TOS, is used for testing overextension trips and ERS functions, especially when the loading arm must be moved to a dummy manifold beyond normal alarm limits. TOS may override movement restriction beyond pre-alarm and may override actual ESD-2 action from proximity switches during testing. It must not suppress alarms, and it must not override ESD-1 where ESD-1 remains required. TOS should be key-locked, locally indicated, shown in the main control room, and controlled by permit. Loading movies should not be openable when TOS is active. The override should remain active until the arm is returned through the pre-alarm area into the normal operating envelope. Testing proves the system. If you do not test the ESD system, you only have a drawing. Testing must cover initiating devices, final elements, logic, hydraulic circuits, inhibiting devices, alarms, overrides, ERS valves, emergency release couplers, loading MOVs, ship shore link, and push buttons. For ESD-1, test low hydraulic pressure, ship shore link connection and disconnection, loading arm pre-alarms, surge drum high level, fire alarm simulation, emergency push buttons, pendant box push button, fuse failure where applicable, and ESD valve operation. ESD-1 valves should be tested at the start of each loading. Valve tightness should be checked during maintenance shutdowns. For ESD-2, test overextension trip simulation, protected push buttons, loading MOV position switches, 2-position mode switch, storm lock switch, solenoids, ERS valve closure, and actual dry brake function. Actual dry brake testing is not routine button pushing. It requires skilled supervision because reassembly of the coupler and cylinders needs competence. A practical limit is often twice per year per loading arm, under strict engineering control. If the berth is exposed and vessel movement is significant, testing before each loading may be required. If the berth is sheltered, monthly testing may be acceptable. Testing philosophy must follow the terminal risk basis. Testing during live loading should be avoided. ESD functions should not be casually overridden while cargo transfer is in progress, especially at multi-product or multi-jetty facilities. Any trip function at high or low should normally have a pre-alarm at high or low. This applies to surge drum level, hydraulic pressure, receiving tank level, receiving tank pressure, and ERS hydraulic pressure. Low hydraulic oil tank level may be alarm only. Low nitrogen precharge should inhibit hydraulic pump start until adequate precharge is restored. Alarm lights should be duplicated in the main control room and jetty control location. Operators must clearly know whether the system is healthy, tripped, overridden, inhibited, parked, live, connected, or ready. So the full ESD system is not one device. It is a coordinated architecture. It includes ship-shore communication, ESD valves, pumps, spillback, loading arm monitoring, ERS isolation, dry brake release, surge relief, hydraulic backup, fail-safe logic, manual initiation, automatic initiation, alarms, overrides, interlocks, reset philosophy, and test discipline. The real quality of the design appears in the sequence. Which valve closes first? How fast does it close? Does surge remain within design? Do pumps stop correctly? Does spillback open? Does ship and shore shutdown coordinate? Does ERS isolate before uncoupling? Does the arm move clear after release? Does the logic latch? Can the operator identify the cause? Can the system be reset only after correction? Can an override defeat protection? Can a parked arm accidentally release? Can test mode be left active? These are the questions that define the engineering. For design engineers, the task is to define the shutdown philosophy, surge basis, valve behavior, interlocks, and failure response. For instrumentation engineers, the task is reliable signals, clear logic, meaningful alarms, visible overrides, and testable final elements. For mechanical engineers, the task is loading arm envelope, ERS mechanics, storm locks, coupler release, actuator behavior, and post-release movement. For process engineers, the task is flow direction, pump response, spillback, relief, receiving tank protection, backflow, line pack, and transient pressure. For operations engineers, the task is to know exactly what will happen before pressing the button. For maintenance engineers, the task is to prove that the system still works after corrosion, vibration, hydraulic leakage, aging solenoids, weak accumulators, and field modifications. The lesson is direct. Do not design ESD-1 as a panic stop. Design it as a controlled transfer shutdown. Do not design ESD-2 as a dramatic release. Design it as sequenced isolation and dry brake disconnection. Do not treat surge as a secondary calculation. Treat it as a governing design constraint. Do not treat the ship-shore link as an accessory. Treat it as the shutdown coordination backbone. Do not treat overrides as harmless. Treat them as controlled exceptions. Do not treat testing as paperwork. Treat it as proof. LNG and LPG transfer systems do not forgive casual engineering. Ships move, valves fail, power fails, hydraulics leak, operators make mistakes, signals disappear, pumps trip, weather changes, surge happens. A properly engineered marine ESD system does not merely shut things down. It preserves control when control is being lost. And in high-consequence transfer systems, safety is not a button. Safety is architecture. Safety is sequence. Safety is discipline, like share and subscribe for more technically sharp engineering design and implementation podcasts. Follow for practical lessons in automation, instrumentation, control systems, process safety, project execution, and engineering management.